Good morning, students. Welcome to Lakshya Academy YouTube channel. We completed how a PN junction diode can form and forward biasing of a PN junction diode, reverse biasing of a PN junction diode, and the special type of a PN junction diode, which is Zener diode. We completed that part. Okay, for the purpose of numericals, and I explain some part. First of all, this is the symbol of a PN junction diode. Actually, this is P-type semiconductor and this is N-type semiconductor. Okay, so this behaves as anode and this behaves as cathode. In the market, the PN junction diode looks like this, and they are very small in size. They are sturdy, so they can used in microcircuits. This is the symbol of PN junction diode. This is the symbol of Zener diode. Symbol of Zener diode, anode and cathode mentioned in the diagram. A PN junction diode can be used as a half-wave rectifier. A rectifier means which convert AC to DC. The efficiency of half-wave rectifier is the ratio of output DC power to the input AC power. The ratio of output DC power to input AC power. Efficiency is denoted by eta. This is eta. Efficiency is denoted by eta. So eta equal to output DC power divided by input AC power. Efficiency of half-wave rectifier is the ratio of output DC power to the input AC power. Actually, in the syllabus we don't have the derivation of efficiency of half-wave rectifier. So I am not going to give the derivation, total derivation. Efficiency of a half-wave rectifier can be given by eta equal to 0.406 into RL by RL plus RF. 0.406 into RL by RL plus RF, where RL is load resistance. RL is load resistance and RF is resistance of the diode when it is in forward bias condition. RF is resistance of diode when it is in forward bias condition. So efficiency of half-wave rectifier is given by eta equal to 0.406 into RL divided by RL plus RF. Okay, note down that. Next, a rectifier is the circuit which converts only one half of the cycle of alternating current into direct current output is called as a half-wave rectifier. There are some advantages of half-wave rectifier. it is cheap and it requires very few number of components to construct, and in the circuit design it is easy to construct. Okay, and next, disadvantages of half wave rectifier. Along with the advantages, there are some disadvantages of a half wave rectifier, and those are: the power delivered only during one half of the cycle only. Therefore, the power output and rectification frequency is very low. Power output is very low in the case of half wave rectifier. That is one of the disadvantages of half wave rectifier. And transformer utilization factor is very low. Maybe you have the doubt that what is transformer utilization. So actually the total concept we discuss in that AC currents chapter separately. So time being, you note down that transformer utilization factor is low in the case of half wave rectifier. And the DC output power produced from the half wave is not satisfactory to make a general power. These are the disadvantages of half wave rectifier. Next, a PN junction diode can also be used as a full wave rectifier. The efficiency of full wave rectifier is also defined as the ratio of DC output power to the input AC power. So efficiency eta is given by P DC divided by P AC, DC output power by AC input power. Efficiency of full wave rectifier. In full wave rectifier, 2 diodes are used, and in some of the special cases 4 diodes can also be used. That is not included in our syllabus. The efficiency of full wave rectifier is given by eta equal to 0.812 into RL by RL plus RF. So where RL is load resistance and RF is forward bias resistance. Advantages of full wave rectifier. The output and efficiency of center tap full wave rectifier are high because AC supply delivers power during both the halves. We are getting output during both the halves, positive pulse and negative pulse. So efficiency is more than that of half wave rectifier. For the same, secondary voltage bridge rectifier has double output. Okay, this has a double output than that of half wave rectifier. And disadvantages of full wave rectifier. Generally, compare with the half wave rectifier, full wave rectifier requires more number of diodes. For the center tap rectifier that we discussed in the previous part, for the center tap rectifier we need 2 diodes, and for the bridge rectifier we require 4 diodes. Bridge rectifier not included in our syllabus, so that's why I didn't give that circuit diagram of that bridge rectifier. When a small voltage is required to be rectified, the full wave rectifier circuit is not suitable. For the small voltage required, a half wave rectifier is better than that of full wave rectifier. Okay, these are the disadvantages of a full wave rectifier. Yeah, differences between full wave rectifier and half wave rectifier. Some of the factors I have given, and we can discuss the RMS values of current, RMS values of voltages, and average values of voltages, because here we are considering the AC input. For AC input, we have to study the RMS value of current, RMS value of voltages, and peak value of voltage and peak value of current, and average value of voltage, average value of current. Those all the things I didn't give here. Yeah, for the half wave rectifier, the number of diodes can be used is 1. For the full wave rectifier, 2 or 4. For the bridge rectifier, we require 4 diodes. For center tap rectifier, we require only 2 diodes. Yeah, form factor. For the half wave rectifier, the form factor is 1.57. For full wave rectifier, form factor is 1.11. The rectifier efficiency is 40.6% in the case of half wave rectifier, and in the case of full wave rectifier, the rectifier efficiency is 81.2%. And for half wave rectifier, the ripple factor is 1.21, and for full wave rectifier, the ripple factor is 0.482. Okay. So what is the ripple factor and a form factor, that we discuss in detail in AC circuits chapter. Next, Zener diode. So it is a Zener diode is a reverse biased heavily doped semiconductor PN junction diode, exclusively operated in breakdown region. Yeah, actually Melvin Zener, American physicist, and he invented the Zener diode. Clarence Melvin Zener, American physicist, invented Zener diode. Yeah, Zener diode. Zener diode can be used as a voltage regulator. This is the circuit diagram of Zener diode. This is the symbol of Zener diode. Okay. To the Zener diode, a series resistance is attached. Series resistance. A load resistance is attached across the Zener diode. So output can be measured across load resistance, output voltage across Zener diode equal to voltage across load resistance can be measured by the voltmeter V2. Okay. Actually, a variable source is given to change the input values. Here, and the input can be measured by using the voltmeter 1. This is voltmeter 1. So here VI is input voltage. VI, input voltage. II is input current measured in the ammeter. Here the current II divided into two parts, IZ and IL. So here we can apply Kirchhoff's current law. Total current II equal to IZ plus IL. IL is current passing through the load resistance. IZ is current passing through the Zener diode. Got it? Okay. So VI, II and RI, RL, VZ, IZ, IL, V output. These are the parameters involved in Zener diode acts as a voltage regulator. Okay. Yeah, I have explained the parameters. First one, VI, input reverse bias voltage. Input reverse bias voltage. And VO, output voltage. And RI, input resistance. RL, load resistance. II, input current, reverse current. IZ, Zener diode current. IL, load current. So II equal to IZ plus IL. From that we can write IL equal to input current minus Zener diode current. IL equal to II minus IZ. Next, V output, VO equal to VI minus RI into II. At breakdown, increase of VI value increases II by large amount, so that V output equal to VI minus RI into II becomes constant. So this constant value V0, which is the reverse breakdown voltage, also named as Zener voltage. Okay, V0 remains constant. Actually, this information is important for the problem solving purpose. Yeah, Zener diode as a voltage regulator. Just now we discussed about that. There is a series resistance connected to the circuit in order to limit the current in the diode. It is connected to the positive terminal of the DC, and it works in such a way that the reverse biased can also work in a breakdown region. And we do not use ordinary junction diode because the low power rating diode can get damaged when we apply high reverse bias voltage. Since the input voltage and the required output voltage is known, it is very easier to choose a Zener diode with a voltage appropriately equal to the load voltage, VZ equal to VL. Okay, so by knowing the input voltage and required output voltage, we can choose which Zener diode is suitable to our experiment, whatever may be. Yeah, differences between an ordinary diode and a Zener diode. Ordinary diode obeys Ohm's law. Zener diode does not prefer Ohm's law. Actually, the level of doping is low in the case of ordinary diode, and the level of doping is very high in the case of Zener diode. and the basic diode will be limited in forward biasing, and the conduction is evident in both forward and reverse bias conditions in the case of a Zener diode. And ordinary diodes can be used in rectifiers, and Zener diode especially useful in controlling the voltages as shunt regulators, voltage regulators. Yeah, while discussing the concept of a Zener diode, and we have to focus on two factors. One is Zener breakdown and another one is Avalanche breakdown. Okay, an electrical breakdown can be explained by the two phenomena. One is the Zener breakdown and Avalanche breakdown. Yeah, what is meant by a Zener breakdown? When a diode is in reverse biased condition, the kinetic energy of the electrons increases. So, if the kinetic energy of the electron increases, they move with high velocities. These high velocity electrons may collide with the atoms and give rise to free electrons. So these free electrons give rise to a high value of reverse saturation current. Okay, so when it is reverse biased, kinetic energy of electrons increases. Because of kinetic energy increasing, the velocity of electrons increases, they collide with the atoms and free electrons released, so saturation current increases, reverse saturation current increases. So this is known as Zener breakdown. What is Avalanche breakdown? The Avalanche breakdown occurs when a high reverse voltage is applied across the diode. Very high reverse voltage is applied across the diode. As we increase the applied reverse voltage, the electric field across the junction increases. This electric field exerts some force on the electrons at the junction, and this force frees them from the covalent bonds. So these free electrons start moving with high velocities across the junction and collide with the atoms. Yeah, applied voltage is more, electric field across the junction applies or exerts some force. Because of this force, electrons move with high energy, and these free electrons start moving with higher velocity across the junction and collide with other atoms and further create further number of free electrons. So if number of free electrons available is more, obviously conduction increases. There is observation of rapid increase in the net current value. Okay, both these breakdowns occur in Zener diodes only. So this is called as Avalanche breakdown. So compare with the Zener breakdown, the applied voltage is more in the case of Avalanche breakdown. Yeah, in the diagram, and I show the breakdown, Zener breakdown region and Avalanche breakdown region in reverse bias condition. And Zener diode acts as a regular diode in forward bias condition. The Zener diode has the special peculiar property in reverse bias because it is heavily doped. Yeah, differences between Zener breakdown and Avalanche breakdown already we discussed about that. And this Zener breakdown is observed voltage 5 to 8 volts, and Avalanche breakdown is greater than that of 8 volts. The valence electrons are pulled into the conduction band due to high electric field in narrow depletion region, and the valence electrons are pushed to the conduction band due to the energy imparted by the accelerated electrons, which gain their velocity due to their collision with the atoms. The increase in temperature decreases the breakdown voltage. This is the very important concept. The increase in temperature decreases the breakdown voltage. In the case of Avalanche breakdown, the increase in temperature increases the breakdown voltage. And Zener breakdown can be observed in the case of highly doped cases, and Avalanche breakdown can be observed in the case of lightly doped cases.